So over the last week or so, we have been talking a lot about torques, turning effects, if you will, things that make things rotate. And today I want to take this into even more dimensions and unit vector notation and all of that good stuff. So, here is a rotating object. It's going to rotate about this axis of rotation right here. And we're going to apply a force here. That force is being applied a distance r away from the axis of rotation. Right? And so this is the force and this is r. And if we put those two together, we can calculate a torque. But let's remember that since these aren't perpendicular to one another right now, we need to know the angle in between. And to find the angle in between, you must draw two vectors tail to tail. So if I take my r and I draw it out here, tail to tail with f, that would be the angle in between. And then, as we have defined, we know that the torque is Rf sine theta, the magnitude of that distance, the magnitude of the force, times the sine of the angle in between. But realize what you're doing here. R is a position vector. Right? It's a vector quantity. F is a force, which is also a vector quantity. And you are multiplying these two things together and getting out a third vector, the torque. So this is actually the third kind of vector multiplication that we have seen this year. We started out, and even last year, doing a lot of scalars times vectors. Think of the kinematic equations, 1/2 at squared, right? Where the 1/2 and the t squared were scalars, and the a, the acceleration, was a vector. All that did was it changed the magnitude of the vector, but it didn't change the direction of it. Right? Multiply a scalar times a vector. And then in the energy unit, we did work, right, which was F dotted with D, FD cosine theta. Right? That was multiplying two vectors together, the force and the resulting displacement, and getting out a scalar. It's called the scalar product, right? The dot product, if you will. An amount of work, an amount of energy transferred into or out of the system by means of the external force. Well, here we're doing torque, and we're multiplying two vectors r and f together and getting a third vector out, which is the torque. This is called a vector product, or a cross product, because of the symbol we're going to use. Okay? The math definition's great right there. The product of two vectors that result in a third vector that is perpendicular to the plane containing the original vectors. Woo-hoo. If you think about the torque vector is perpendicular to the plane containing r and f, right? Because you rotate around the vector. If you think of the right-hand rule, your outstretched thumb. Really, the vector product, or the cross product, if you will, is a measure of how perpendicular the two vectors are. Right? The dot product was a measure of how parallel. FD cosine theta. Right? Cosine theta is a maximum when theta is 0. Right? So when they're parallel to one another, you get you do the most work, you transfer the most energy. In terms of torque, right, you want them to be perpendicular to get the most torque out. Right? So let's say we had a vector A and a vector B with an angle theta in between. Right? Then just generically, right, we would say that the cross product of A and B is AB sine theta. Now, notice the symbol here, the cross, the X, if you will, for this. So you could read this as A cross B, or the cross product of A and B, or the vector product of A and B is the technical terminology. Right? This doesn't give the direction, it gives the magnitude of the resulting vector. The direction we'll talk about in a second. But notice this is the magnitude of vector A, the magnitude of vector B, and the sine of the angle in between. Okay? Now the direction is going to be given by our right hand rule. We are going to take the fingers of our right hand and rotate the first vector in the listing into the second vector. So you have to rotate it. Right? So imagine using your fingers to push A into B. Hopefully your thumb is pointing out of the screen right back at you right now, right? If you take A into B, your thumb should be pointing right at you. That's the vector product. That's the direction of the vector product. Note that out of the screen is perpendicular to the plane containing A and B. A and B live here in the plane of the screen. So the torque vector, or in this case just the cross product if we're being generic, right, has to be perpendicular to that. Cross products are always perpendicular to the plane, or the vector resulting from a cross product or a vector product is always perpendicular to the plane containing the original two vectors. Rotate the first vector into the second vector. Now, you'll notice that this is not commutative. If you rotate B into A, hopefully you're doing this with your right hand, fingers of your right hand, what direction is your thumb pointing now? Into the screen, right? Negative. So it's not commutative. Okay, the scalar product is commutative. Okay, the dot product, if you will, when we do work. Doesn't really matter what order we do it, but the cross product is not commutative. The order is very important. Right? And that's because you're creating a third vector. Right? So this is not commutative. So here's a little picture that maybe this will help. Okay, if R and F are in the horizontal plane, okay, the plane of like a tabletop, okay, then this is R into F. See how the fingers here in the picture, right, are rotating R into F, and your thumb points straight down, right, straight down, which would be a negative torque, if you will, right. Notice that would make it rotate clockwise. Right? Clockwise is negative. So everything's consistent with what we did before. Okay. Fingers of your right hand to rotate the first vector into the second vector through the smaller angle between. So we would then write the torque in all of its three-dimensional glory here as the torque is R cross F, or the vector product of R and F, and you have to write it in this order. Okay, it's R into F, not the other way around, right? You'll get the opposite answer. So make sure you get these in the right order. You've probably seen me write it that way, right, in other problems beforehand, even if we weren't dealing with it in its full vector nature. So let's do a couple of examples here. And of course, we're going to do some three-dimensional or some unit vector notation here. I'm going to do some two-dimensional problems so that we can draw them on the screen. But in your homework, you might have to do as many as 3 dimensions. Ooh. So here we have a force given by F equals 3.0 newtons I cap plus 4 newtons J cap, unit vector notation, acts on an object, and it's located a distance r, or 1.0 meters I cap minus 2.0 meters J cap, away from the axis of rotation. Right? So r, remember, is the distance from the axis of rotation to the point of application of the force. And I want to know, how much torque does that force provide? Okay, can I calculate that torque? Well, 2 methods to do this. One is to kind of turn it into a problem that we've done in the past, and we're going to kind of grind through this method. And the other one will be using unit vector notation. I'll show you that second. So first off, R cross F for torque is really magnitude of R times the magnitude of F times the sine of the angle in between. But we don't know the magnitude of R or the magnitude of F or the angle in between because these are written in unit vector notation. But we can certainly see all those things if we draw them out and do some trig, some geometry. Right, so if we want to draw out F, 3.0 newtons I cap, right, would be to the right because it's positive, right, and 4.0 newtons J cap would be up. Notice head to tail is plus. So that is the actual vector F. From the tail of the first to the head of the last is the resultant. So this is actually vector F. And it's in the IJ plane, which is the plane of the screen, or the XY plane, if you will, the plane of the screen. Right? This is the angle. I'm going to call this phi because this is not the theta in the equation. Right? This is just an angle we need to be able to name everything later. Well, we happen to know what f of x and f of y are. Right? 3.0 newtons and 4.0 newtons. So we can do a little Pythagorean theorem, right, to get 5.0 newtons for the force. And then we can do a little inverse tangent of opposite over adjacent, and we get 53.1 degrees, keeping an extra sig fig running around until the very end. So this is taking our vector f in two-dimensional unit vector notation and putting it into polar coordinates, or magnitude and direction, as it's often called. We now have to do the same thing with the vector r. That's 1.0 meters I cap, which would be to the right, positive, And then minus 2.0 meters j cap means down, right? Or a negative, plus a negative, if you will, right? And so then the resultant goes from the tail of the first to the head of the last, which is vector r. So whatever our object looks like, right, here's our axis of rotation, and here is where we would be applying the force. Right? We'd be applying a distance r away from our axis of rotation, if you will. Since we know what rx and ry are, the components, I'm going to call that phi as well, different angle, right? We can do a little Pythagorean theorem, 2.24 meters, and a little inverse tangent, 63.4 degrees. So now we know both vectors in magnitude and direction form, polar coordinates if you will. So we can draw them out and finally find the answer. Right? There's r, right? That's 63.4 degrees. There's f, there's 53.1 degrees. This is the angle in between, so that's actually theta, which is 116.5 if you add the two together. Note, I drew these two vectors tail to tail, which means this is the angle in between. Technically, f acts here, right? Because that would be the point of application of the force, right? But we can't do the trig on that, so we have to draw them tail to tail to see the angle in between. So, r cross f is rf sine theta. We now know what all those things are. So we plug in r, which we found is 2.24 meters, f, which is 5.0 newtons, and the angle, which is 116.5 degrees, and we get 10, with a decimal point to 2 sig figs, Newton meters. Could you write it meter newtons? I suppose so, but traditionally it's written Newton meters, even though we have to do it in this order, please, right? Now, what direction is that? Well, look at the picture here. You can use the right-hand rule. You can take the fingers of your right hand and rotate R into F. In what direction is your thumb pointing? Remember, you got to go in order, so R into F. Your thumb should be pointing out of the screen, right? Well, in 3 dimensions, out of the screen is the z-axis, or in unit vector notation, it's k cap. And since it's out of the screen, it's positive k cap. Right? It's out of the page, or positive k cap, right? This would be a counterclockwise torque, right? And it's positive, right? Fingers pointing out of the page. So if you will, you could see this as positive k cap. Note here, right, we have ij plane. Both of these vectors live in the ij plane. So the torque vector has to be perpendicular to that plane. See how that works? Perpendicular to the plane of the screen is in or out, which is k cap. I know, it's complex stuff, this vector product. It's good that it's the last one of the 3 types of multiplication in vector algebra. So let's do method 2, which is the full-on unit vector notation deal here. So we have r cross f. Let's write in r and f in unit vector notation. And then just like any multiplication, it's like we're multiplying 2 binomials together, right? So we can FOIL these. And of course, since you're doing 2 binomials, you're going to get 4 terms. In your homework, you're going to do a 3 by 3 unit vector notation. Right? So if you're multiplying 2 trinomials, you're going to get 9 terms. But if we work everything out here, right, and make sure you're writing things in order, so we get 1 meter times 3 newtons, I crossed with I. 1 meter times 4 newtons, I crossed with j. Do you see how I have to put this in this order? Be careful that you're doing it in the order, right? So this to this. And then we go to this one, which is negative 2 meters, 3 newtons, j crossed with I. And then negative 2 meters, 4 newtons, j crossed with j. Okay, again, if you're doing a 3 by 3 in the homework, you're going to get 9 terms out of here. Well, of course, these coefficients, right, are just scalars, so we can just do normal multiplication to put them together. But then the question is, what do we do with these cross products? Well, first off, remember here, these are unit vectors, and the whole point of a unit vector is that it is 1 unit long, hence the name. So it's 1, right? Got a magnitude of 1, but what's the direction? Right? How do we do this? Okay, well, let's look at the ones that are the same, the I crossed with I and the j crossed with j. What's the angle in between? Right? If torque is rf sine theta, Well, if they're the same vector, the angle in between is 0. And the sine of 0 is 0. So 1 times 0 is 0. So those two terms cancel out. If you're really good and you're thinking about scalar products, amounts of work that we used in energy, you might remember it was the other ones that canceled out, right? The perpendicular ones canceled out because we were using a cosine. That was how parallel they are. This is how perpendicular they are. Remember that when your force acts through your lever arm, you don't get any torque. So if your vectors are acting in the same direction, your components are acting in the same direction, you don't get any torque out of those, is basically what the math is saying. Okay? So we put together what we have left, and we get 4 Newton meters I crossed with J plus -6 Newton meters J crossed with I. Now, we don't get numbers out because this isn't a scalar product, it's a vector product, so we need to get a vector out. So the question is, what vector can we replace I cross with J, and what can we replace J cross with I with? Well, let's think about this. 3-dimension right-handed coordinate system, right? There's I cap, there's J cap, there's K cap. So if you're going to use the right-hand rule, I into J, take the fingers of your right hand, rotate I into J, and what direction is your thumb pointing? Straight out of the screen, which is positive K cap. What about J cross with I? Well then, fingers of your right hand, rotate J into I. Those are both, remember, in the plane of the screen. And now what direction does your thumb point? Into the screen, which is negative K cap. Now, when I learned this back in freshman year of college, 1987, this is what my professor taught us to help us remember how to deal with I, J, K. Okay, so let me explain what this is. If you take I, J, and K and you write them down in alphabetical order, right, a little triangle like this, if you're going around this way, you get the next one positive. This is what I mean. I crossed with J is positive K. I crossed with J, your thumb points out of the screen. J crossed with K is positive I. K crossed with I is positive J. You see what I'm saying? Going around in this order. Okay? I mean, you can do the little right-hand rule all the time, and believe me, in like calc when you're learning this, and in physics when you first learn this, on that test, you often see people with their right hand out. Hopefully they're right, because if they're doing their left, everything is backwards, right? And you see people trying to rotate the fingers of their right hand to figure all this out. But this little thing here works. Right? If you're going the other direction, you get the negative next unit vector. So as we showed here, J crossed with I is negative K. Do it with the right hand. Rotate J into I, and your thumb points into the screen. Rotate J into, I'm sorry, we're going this way. Rotate K into J. K is sticking out of the screen. Rotate it up to J, and your thumb should be pointing to the left, which is negative I cap. Now, the only thing that's weird about this is that it's completely opposite of our counterclockwise is positive, clockwise is negative rotation rule, but this isn't a rotation thing. This is a vector algebra thing. Sorry, rules are different. You just got to memorize it, right? Or you got to think through how to do these, okay? So I would suggest remembering this in case faced with a unit vector cross product problem, vector product problem. So in this case, I crossed with J is positive K cap. J crossed with I is negative K cap. And since these are like terms, well, the negatives cancel here, right? So we end up with 10 Newton meters positive K cap. Isn't that exactly what we got before? Now, if you can do this, this I think is faster than our first method. Okay, but it utilizes a whole lot of vector algebra. It's just something you got to practice. Okay, and like I said on your worksheet, I'm going to have you do a proof, kind of like I did with scalar products, where you're going to do three-dimensional unit vector, and you're going to kind of prove the equation you get out. Although believe me, vector products, you do not get as nice of an equation out as you do with scalar products, if you remember that one. Okay, so just the way you got to deal with it. So remember this little thing to help you figure out, right? If you're going around this way, you're going positive next one. If you're going around the other way, you're getting the negative next one. Right? And it goes I, J, K. That's the way I was taught, at least.